Hello everyone and welcome to this next lecture in the electrical machine simulation series, and this is where we had left off in the previous lecture where we had done a basic simulation with a current source which in turn is represented by a voltage source in series with a resistance. However, we had not included any control, so we had just gotten a basic current waveform. Specifically, this is what we had got. So this is essentially because the variable resistance remains at its initial value of 100 ohms and we have an AC voltage source of 240 volt RMS, which corresponds to around 340 volts peak. So therefore we have a current of around 3.4 amperes. Now in this lecture, we are going to introduce control so as to be able to produce any current that we want. So let's get started with that. So as always, before I start the lecture, a little bit of brief background that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses which you can access through my own website pythonpowerelectronics.com. That is basically the name of the project.com. So here there are these 4 buttons: download, learn, watch, read. So all you have to do is click on this learn button and that takes you to the list of my courses. So the very first course which I have is simulating power electronic circuits using Python, and in this I talk about the basics of how we can use Python to simulate power electronic circuits, and specifically how we can use Python Power Electronics open source circuit simulator. So the course can be found on clicking on this link where it is hosted on Udemy. The second course is on basics of digital signal processing for power engineers, and in this I talk about how you can use Python for implementing, designing and analyzing filters using Python, specifically the signal package in SciPy. The next course is simulation of magnetics for power electronics using Python, and in this I talk about how you can use Python and Python Power Electronics to simulate magnetic components such as inductors, coupled inductors and transformers. The next course is control analysis with Python for grid connected converters, and in this I talk about how you can use Python, specifically the Python control package, to implement, design and analyze the performance of controllers for specifically power electronic applications. And the very latest course I have is a completely free course which is called Why Specialize in Power Electronics, and this is targeted towards young undergraduates or even high school students who are looking towards finding out more about which domain they should specialize in, and this talks about some of the challenges and opportunities in power electronics. So to check out any of these courses, all you have to do is click on any of these buttons and that will take you to the course link, which for now is on Udemy. The link for this page is provided in the description for this video. Do check it out if you are interested. So let me get back to the lecture. So this is where we were. Let's go and have a look at the circuits. We had 2 circuits. So one is the resistive load. This is where we had connected an AC voltage source to our load, right? And we are measuring the voltage, of course. Now this load here has been taken into another schematic. The reason is because we can then expand it to how much ever detail we want. And here I talked about how we have represented as a current source. So you have a control voltage source in series with a variable resistance. Now let us introduce some control here so as to be able to produce any current that we want. So let's go over to our editor and let's start writing some control code. So the first thing we want to do is let's write out what we want to do. We want to generate, or rather draw a current equal to any given reference, right? Let's call this reference as IREF, right? Just an example, you can call it anything you want. So this is what we have. So I could give this any value, and the objective is that we have to be able to produce such a control output voltage and such a resistance to draw this current. That's our objective. So let's go back to our web browser and go back to the main page and go to edit control and configure control. Now the first thing we need to do whenever we are writing any kind of control is, unless it is a really simple control, if you need any form of integration or any form of mathematical computation, it is always advisable to run your control code at a specific time interval. right? So that then you have more control over it. You know how often you are controlling it. And if there is any analytical component like signal processing, you can then design it with that time interval in mind. So let's go and add a time event. So the first time event is basically time event variable. We can call it time event T1, and the initial time event is at 0, right? So because we wanted to start it right away. So all we have to do is we have to introduce this in our control code. So the way we do this is we say T clock. T clock is the current time instant of the simulation. This is provided by the circuit simulator, Python Power Electronics. You don't have to worry about it, right? Any control file will have this variable T clock, which gives you the current time instant of simulation. So when this T clock is greater than or equal to T1, in that case, we want to write a control code. So that means, let me put it there. This is where our control code or load model, however you want to call it. And of course, once you are running your control code, at the end of your control code, you must update your time event. Now, of course, to update the time event, we need a time sample. So let me put a time sample. Now, in this case, since this is not actually a control code, but rather more of a load model, I would like to run this at the same time instant as the time of my simulation. So therefore, I will put this as 1.0 e raised to minus 6, because that is the time instant of simulation. So I'll just say control time interval equal to integration time step, right? Because this is not really a control file, this is more of an actual mathematical model. And I will update it by this control time interval or integration time step, right? So we are running it at the same speed as our actual integration solver, right? Numerical integration solver. So now that we have this, we have now a basic time interval. So let's keep going. The next thing we need to do is we need some inputs. So let's go back to our circuit and see what we need. So as we already said, this is the voltage which is being measured, right? Now this voltage which is being measured and this voltage that is being generated with respect to this resistance will produce a current, right? So now if I were to write this Kirchhoff's voltage law along this loop, right, what would I get? Let's call this V measured. Okay, so let me now add this control input. So let's say I have voltmeter load. Let me just check which voltmeter it is. It is voltmeter current 1 source 1. So I need this one. And let me call this V measured, or I'll call this V terminal, right? And let me go and copy this and paste it in my editor. So if I were to write this Kirchhoff's voltage law, and of course, as I already said, that the positive terminal of this voltmeter is upwards, right? So that means if I apply Kirchhoff's voltage law in the clockwise direction, this will be taken as positive. And if we take this control voltage source with a positive polarity upwards, it becomes negative. And of course, if the current we are taking as the downward direction, then this current multiplied by the resistor is also negative, because we are in the direction of the current, right? This is Kirchhoff's voltage law. So we say V terminal minus I load multiplied by, I would say, what would I call this? Let me call this series resistor, right? So I'll call this series res is equal to 0. This is our Kirchhoff's voltage law, right? Kirchhoff's voltage law for the current load, for the current source. Now, with this in mind, of course, I've forgotten the control source, of course. How did I forget that? So anyway, this is, what do I call this? I'll call this V source, right? So let's come back here. We are taking V measured minus V source minus I into this resistance is equal to 0. This is Kirchhoff's voltage law, right? We have this equation. Because we have this equation, we can now take this V source to the other side and just copy. I'll just copy this because I'm having trouble typing for some reason. And I'll just delete it here. So this is our equation. That means V terminal is measured. I load is equal to this Iref. So I'm going to replace I load here. Let me write another equation actually. And let me call this Iref. So if we have a particular Iref, right, this is the current that we want. If we use this equation, that is, this is the measured voltage minus this desired current into the series resistance, then this is the voltage that needs to be produced by this controlled voltage source. This is what we need, right? So let's implement this. So we have already put in this V terminal, so we don't need to do anything more. What we need to do, we need to generate this reference. So let's go do that. Let me go back to the web browser and put a static variable. So this static variable, let me call this Iref, right? And let me come over here to my editor and give it a value. So of course, all control code, anything that we are computing should be within this block that is within our control code. Because remember, these are all things we are computing. What remains above this are all constants. Constants are basic parameter calculations which we may need to do, because later when we include machines, we will be calculating the parameter of those machines. So let me give it a value. So Iref, let's say we want 10 amperes, right? And we want to do, I need of course a sine function. So let me import a sine. Let me go all the way up. Import should preferably be all the way on top. Let me import the math module. So we have sine, and with this sine I want to say that I want to produce a 50 Hertz sine wave. So once again, let me define these constants. Let me come over here and say frequency is equal to 50, and let me say Hertz. So which means omega is equal to 2 into math.pi into 50. And let me call this rad per second. And let me just tab it out. So we have defined the frequency of operation, and we've defined the omega, which is the angular frequency corresponding to the frequency of operation. So I can just use this omega, paste it here, and say that this is equal to t clock, that is the current time instant of the simulation. And if you want, we can give it even a particular phase angle difference. For now, let's not do it, because now we already have a voltage source which is a sinusoid. So a current is also in phase with it, right? So our current and voltage will be in phase. Later we can introduce a phase angle difference and see how that works. So we have now produced a static variable. Now with this static variable, we now have to now produce this voltage source, and we have to write this equation. So let me go over and let's add another static variable. We can directly add an output variable, but I would rather do it this way. And let's call this V source. So let's go back here. Since it's the same equation, I can just go copy this and place it here. Actually, this should be the very first line because that is a comment. Let me place it here. So we are now generating the reference current, and we are calculating the terminal voltage with respect to this resistance, this reference current. Now there's one problem which we need to solve, and that problem is we need to figure out our control output. So this is our series resistance, right? We have to produce this series resistance. So I would take this series resistance, copy it, and place it here. So this series resistance is what will be included here, right? So now this series resistance has a 100 ohm value, right? If you come back here and have a look, this initial output of the series resistance is 100 ohms. For now, we leave it as it is. Later on, I'll tell you what the significance of this value is and how you would typically adjust it in any system. But for now, 100 ohms is good enough. So if we come back here and have a look, we have now said that our voltage source, this is the static variable, is equal to the measured voltage, right? This measured voltage, and if you come back here and have a look, this is the input voltage, which is the measured voltage, is this measured voltage minus the desired current multiplied by the series resistance, right? This series resistance is basically this output variable resistance. So just to avoid confusion, I'm going to go and copy it here as well. There's no need to introduce another variable because this is what we are using anyway. So we have now calculated the voltage source. So what do? I have to now hook this up to the actual output variable. I have to hook this up to this control voltage source because this is the voltage we have calculated necessary to produce this reference current. So this needs to be linked with this output voltage. So let's go back to our web browser. We have already defined our control voltage source output by this variable. So all I have to do is go back here and equate this to our voltage source, right? So now that we're done with this, we need, of course, it would be nice if we can plot some values. So let's go plot this reference. So I'm going to add a variable storage element. What is the name of the file? The name of the file is load variation. So let me call this load var iref. Initial value is 0. Storage status, yes, because I want to plot it. So let me save the value. And let me go all the way down. Add a variable storage. I'll call this load var. And here I'll say V out. This is the actual voltage that we want to plot or we are generating. So let's go and copy this variable, come over here, equate it, copy the other variable, come over to the editor, equate it. So the first one will be the reference that we are generating. The second one is the output that we are generating. This can also be V source because they are the same thing, but maybe we should make it V source because it's a static variable, right? Let's do that. So with this, we now have a very, very basic control file. So let's go back to our web browser and run this. So it says simulation is running. Always go to the command line, make sure there is no error. There is no error, so that means the simulation is indeed running. So let's go back to our web browser and let me save this as another variable, right? Because I'm going to plot it again. So let me go back to my web browser and click on the plot button. And let me go back to the file browser and check out what this is. And you see now we have 10 amperes, right? We have 10 amperes. Let me paste, this is the older version because this is, remember, this is what we got before. I want to just compare these two. This was before. Before, when there was no control, absolutely no control, we had just 100 ohm resistance. We were producing a simple 3 ampere current because of the 100 volt resistance. Now I am regulating my control voltage source in such a way that I can produce a current that I want, right? And look at what we want. We wanted a 10 ampere current that is equal to 10 ampere sine omega t. Remember, if you go back and have a look, we wanted 10 into sine omega t, and that is exactly what we are getting here, 10 sine omega t. So the result is we now have a current voltage source that behaves like a variable load, but now we can generate any current we want according to any calculation we wish to make. This is very important because whenever we are simulating electrical machines, we will be calculating certain currents that the machine will draw according to various dynamics, and we'll be producing this current using this method. That is a variable current source which comprises of a variable voltage source in series with a variable resistance. So with this, I'm going to end this lecture. In the next lecture, let us examine this a little more detail and let's play around with certain other scenarios. And we'll also in the later lectures talk about the significance of this series resistance. How do we choose the series resistance and what factors goes into choosing this series resistance to make sure that we have accurate current generation and at the same time we have a stable simulation at all times. So with this, I'm going to end this lecture. If you have any doubts, please do either comment on the video or send me an email or message me on social media, whichever is your preference. Otherwise, I will see you next week where we will continue with this simulation. Thank you so much and see you soon. Goodbye for now.